here for me to be able to speak to our fellow colleagues and also researchers on subjects that are important to structural engineers and students as well. And normally I'm very interested to talk about a few subjects. Moment curvature is one, and modal analysis is another one, and performance-based design and so on. So this one is kind of close to my heart and also related to the heartbeat, so it makes a little bit sense. We have titled the presentation and try to link it to the heartbeat of the structures, just like as the human being, we have the heartbeat. So I think the structures also have kind of a similar property that if we correlate, we can then understand the structural response and the structural health and its potential problems much better. Topic that we have sort of listed here is that we are going to listen to the heartbeat of the structures and understand the modal analysis, and this presentation has been prepared with the help of Dr. Fawad Najm, one of my colleagues and former student here in AIT. Currently, he is in the University of British Columbia in Canada. So some of the details, more details, you can also look at his videos and lectures. So let's begin. First of all, we are going to correlate, like I said, the structural health with the heartbeat of a structure. So looking at the heartbeat of the structure, so basically we are assuming, or we are saying that every structure has a very unique sort of fingerprint or heartbeat characteristics that we can look into. And if, I hope everybody's healthy and then you don't have to go to see the doctor, but as you get older, you normally have to get your checkup every year or every 2 years, or even otherwise when you go, I think if you might have noticed that the first thing they ask you to do is to go and get your blood pressure and also get your heart rate checked. And after that, they will then proceed to do the evaluation of whatever is the cause. Even the dentist, when you go to have a procedure, they will start to check these indicators, these fundamental indicators. So it's so essential to understanding the health of the human being that they are always checked. And similar is true for the structures. And the reason the heartbeat is so essential because of the central position of the heart in terms of our whole health and everything that is derived from there. So the potential sources of any causes of any illness, they can be detected by studying the heart rate and related properties that we will talk about a little bit. So with that in mind, you might have seen, and many of you probably are using the fitness trackers or the smartwatches these days, because this importance of these two indicators has become so prominent that so much wearable devices have been generated and created in the last 1 decade that it is now becoming a universal sort of wearable thing that we wear, like a watch. And a health tracker. And these fitness trackers give us a lot of data, ever-increasing data. And generally, the first thing they measure is the heart rate. And then after that, they can create all these dashboards, weekly, yearly, daily, morning, evening, telling you how did you sleep, how did you perform, you're stressed, you're not stressed, and so on. So a lot of information is derived from basic measurement of a few parameters using these health trackers. So if we take that analogy forward today, we should be able to do a lot of that for our structures as well. So before I go to the modal response, let me go back to the very basic structural response fundamentals before we narrow down to the modal response. And so I presented this before also, so some of you might have seen this slide. But it's essential that we remember where it all started. So it started somewhere in the 15th, 16th century by Galileo when he started observing the fundamentals of the motion and also of the structures. And then, aided by Robert Hooke, he first proposed the proportionality between the displacement and force, and he's credited with starting the stiffness concept at that time. It was also, once again, several hundred years ago. And then we have Isaac Newton, not so far about, coming in, and then giving us the physical connection between the mass and acceleration and force. And then that became very fundamental principles of physics that they still stand. Of course, Einstein's theory of relativity is one thing, but within the gravitational and Earth field, we still believe that Isaac Newton's laws hold. And then we have people like Thomas Young, who started to develop correlations between material stress and strain, and from there onwards, everything accelerated. So let's see what was said by Newton, which basically related the mass and acceleration. So he assumed a body in motion, but rigid body, freely moving, not connected to the ground. So he proposed the mass acceleration force relationship, which is fundamental as one of the laws, physical laws. On the other hand, Robert Hooke and others thought of the structure as being fixed and not really moving, and it was fixed to the ground by a stiffness. So it was connected, the mass was connected to the ground. And then when you combine the two together, you got the first equilibrium equation of moving bodies, but restrained moving bodies. So stiffness, mass, and force were then related in that way, varying with time, of course, because we're looking at the things which vary with time, especially when you're having acceleration in a mass. And then that stiffness alone was later modified to include the damping of the bodies that are holding the structure down and the bodies themselves. So many types of damping came in, but right now we're talking about the basic, structural damping. So we have now K and damping C and mass, and we have the first complete equilibrium equation, including these key parameters. And then after that, we can bring in ground motion. And we say, okay, if there's a ground motion, then we can bring it on the right-hand side, and then we have the first ground motion equilibrium equation. Once again, linear, because all these quantities, although changing with time, they remain linear during the whole equilibrium cycles. And then we went back to Robert Hooke's law, and we discovered, or people could see, that this is an infinite law. That means no matter how large is the force, the displacement is always proportional. So if you, for example, put the force as 1 million tons, you can get a displacement of 10 kilometers, which obviously is not structurally correct, but the relationship states that way. But the observed response of the structure was not this. Observed response was like this. The nonlinear response of the structures, when people tested them, they found that structure actually deviate and then start to become nonlinear and then collapse or break at some point. So with this one, we had the nonlinear response location equivalent to the same displacement, and then from there we can derive the difference between the linear and nonlinear response, and then we can say this is like a correction that we should do to the linear response to get the actual response. Now, it seems very obvious that if we can find the difference between blue line and the linear point, but the problem is that we don't know the blue line. We never know the blue line. We actually have to search for it, and we have to numerically, we can only find by testing, but numerically we can't find it. So we have to search for it. So this becomes a highly iterative nonlinear problem. And if you take this correction, force correction, from linear to nonlinear and put it back into the equations that we know and modify and connect the nonlinearity there, then we have a nonlinear equilibrium equation, static. And then if we bring back the dynamics, then we have the nonlinear dynamic, and then we can finally go to the ground motion, and we have the full ground motion equilibrium situation there. So this gives us the full nonlinear equilibrium system, which we can now solve in most of the software that we have, ETABS and Perform and whatever software they use to get all of the responses. Then, out of that, if you take that whole equation out, it's all varying with time, and you just look at that equation and you try to understand, you can derive a lot of information from their sub-analysis by making some assumptions. For example, you could assume, like this one, we can get the modal response from there by ignoring the nonlinearity, the damping, and the force, and the ground motion. We get that. And we can also get the equivalent static force by making assumptions about the displacement of the acceleration of the mass at the top and the force directly through the mass. And then we can get the response spectrum. We can also get the pushover or nonlinear response by taking the nonlinear portion of the equation. And then we can also get the linear time history analysis. So as you can see in this page, we have everything that we normally do to get the structural response. So this is almost all that we need. Almost. Of course, there are others, but let's say this is mostly what we need. So let's focus on this part, which is what we are talking about today. Let's look at that was for a single degree of freedom that we showed from the figures that I showed you. But for a real structure, obviously we have matrices for mass, we have a matrix for damping, we have a matrix for stiffness, and so on, and everything is a matrix. So when you do all those matrices, then the relationship is modified like that, and then you have external force, you have mass acceleration, you have damping velocity, and you have stiffness displacement, and we have the nonlinearity there. So the whole now structural response is now complete, derived from single degree of freedom all the way to matrices. Knowns are these, and the unknowns are the displacements and the velocities and the acceleration, the derivatives of displacements. So this is the total problem that we as structural engineers are interested to solve. Okay, so now that we have given the overall background of the structural response, let's pick one of them to go into the detail today. And we are picking the modal response today. So modal response is that you have none of these. You have no nonlinearity, you have no external force, and you have no damping. And you are left with just only mass and stiffness and displacements and acceleration. So derivative, second derivative of displacement, stiffness, and mass is the only thing left equal to 0, which basically means it's a natural structure standing by itself, not being disturbed by anybody, made from ideal materials with no damping. So that's the situation that we are in right now. So let's see how we can solve this. So here the knowns are mass and stiffness only, nothing else, which is very, very important for today. And then the unknowns are force. From there we will derive those parameters that at this point we don't know. So the natural response of the structure is of this form. This is a second order linear homogeneous differential equations. And there are a lot of math behind that to solve it, and I do not plan to go into that. You can look at other references. I will just summarize briefly. But for the math, we probably need a separate session, and you can watch some of the videos by Dr. Fawad. He has explained this well. What we are interested in right now is to think of this as the heartbeat of the structure, this relationship. And then this indication of stiffness and mass relationship, we will see what can it give us. Because it's very basic, it's the structure by itself, it's intrinsic, it's just the natural property of the structure, doesn't depend on the loads, doesn't depend on anything. So if you look at the mass over stiffness, the one that Newton and other people, not Newton, the Hooke's law talked about, and if we look at that and the combined equation in motion, then we can actually see that it's a cyclic motion. We can convert that into linear motion through the sine and cos, and we assume that there is a frequency of this oscillation, omega, and from that we can derive through the first and second derivative, and we can find the solution, and ultimately we can come up with the omega frequency to be a ratio of stiffness and mass, square root of that. And that is very important observation, or important derivation from this is a physical solution. The other solution, mathematical solution, also arrive at the same results, but with different assumptions. But I've just presented one of them, and the other one also we will look at later. So having done that, you can see that we can correlate the angular frequency with the translational or cyclic frequency by rotation through the pi, 2 pi. And so this relationship, we can, actually this is supposed to be an animation, but unfortunately we couldn't run it. But anyway, so this is how it works. So you can correlate them through sine and cos and through cycles. And if you go further, so we can now correlate this oscillation with the frequency, and we can say if it completes 2 pi in one cycle, that is one cycle of oscillation. And if we have 2 of those, then we have 2 cycles, and so on. So this omega 1, 2, and 3 gives us an indication of how many times the structure can oscillate in 1 second. So that becomes our basis for deriving 3 important parameters that will define this whole modal response. And this is based on the assumption of the equation that we started with. So there we are. So the natural frequencies and periods, we have 3 fundamental quantities here. The omega, which is the rotational or cyclic frequency, and which is a ratio, square root of the ratio between stiffness and mass, nothing else. So that means if we know these 2 things, this can be computed. And the frequency is derived from there by dividing it by 2 pi, as we see before, and then the period, or time period, some people call it, is then the inverse of that. So now we have a relationship for the time period, or the period, as 2 pi square root of mass and stiffness. And that's it. This is all we need for a single degree of freedom. In fact, and then we can use that to actually now work on many things. So we know that there's a stiffness-mass relationship. So if you want to change or control the natural frequency or periods, all we need to do is change this ratio, not the absolute values. It doesn't matter. The ratio is important. So a very heavy mass with very heavy stiffness or very light mass with very light stiffness may result in the same natural frequency. And this is very important. So let's look at some of these are plots between various mass and stiffness ratios. So this is a mass is about 4 times the original mass on the left-hand side, and then stiffness is same. Then if we continue, then they will oscillate at different time. They have a different period. This has a period of 2 seconds. Let's say the first one has a period of 1, and this one has a period of 0.5, where the stiffness is large. And similarly, on the right-hand side, we have some proportion, and you can see this will oscillate first with a longer period, then shorter period, and then shorter period, because the stiffness is increasing. As the stiffness increases, the natural period reduces, and frequency increases. So that's the basic relationship between the mass and stiffness ratio, and there we are. So we can extend that to a multi-degree freedom system, and we can solve the equation mathematically using it as an eigenvalue problem, and then finding the eigenvectors and eigenvalues, and they give us the natural frequencies and the mode shapes, corresponding displacement patterns for each of the modes. So this is how the programs use it. They use multiple ways to determine these, but eigenvalue analysis is one of them, which is the basic one, the primary one. There are, of course, other methods too. So this gives us the tools now in the programs to do that. Okay, let's go to the multi-degree freedom system. So now you can see here that this is a tall structure with 3 stories, and then it will vibrate first because it's a cantilever, then the second one, and then the first one, because each case the mass stiffness ratios are different, and here they are. And then you'll see that now they start to oscillate in higher modes, as we call them, and that is the first one for the first 3 mass system. And then after that, you will see the second one will start to vibrate, and then back to the further higher modes with more complex mode shapes. So then we have the third, fourth mode shift. So you can see the masses are now moving in different patterns, and each pattern doesn't have real values. These are scaled later to find real values. So we have now a complete picture of the natural frequency or natural period versus the mode shape derived from step by step from single to multi-degree freedom. Okay, so now we are jumping to the full structures and trying to understand what do they mean and what do they tell us and what they can tell us. So this one, so if you play this video, this is a tall building, 40-story something, and it can show you 3 of its primary modes here. The first mode, the second mode, and the third mode. And you can clearly see how the building is oscillating in these modes. And there will be much higher, many modes to come. But these are, let's say, the first primary modes we're looking for in each direction, and so on. So it's a symmetrical building, so it was oscillating like that. So you can clearly see that the first mode has the smallest stiffness associated with that, with the largest movements relative. Second mode will be higher stiffness, smaller movement, higher frequency, faster moving. Third mode will be very fast moving with small amplitudes and very large stiffness. So that's how we can understand them in this way. And then if we have a ground motion, then to get the total response of the structure for the ground motion, all of the responses for many of the modes will be added together, combined with the ground motion in a certain, the way that the structure is moving. It's a complex thing, but physically. So if you can see that these are the sum of the modes will give us the actual vibration of the structure, because those modes are only independent. But when they're combined together, added together, depending upon the ground motion, you will get a certain movement. And that's how you can derive that from that. And we will talk about the ground motion, cause, additive, and all of that stuff. Okay, so modal response now tells us that there is an initial period and there is a mode shape, and both of them come together as a pair, as a set, and there are as many modes in a structure as there are degrees of freedom, because each degree of freedom can move independently when excited with a particular, causing a particular mode shape to be generated. So if there is a structure with 100,000 degrees of freedom, theoretically speaking, there are 100,000 natural periods or modes or mode shapes in that structure. Not all of them are important. We will talk about that. And then local modes are also present there. We will differentiate between global modes and local modes in a while. And then we have to make sure that we understand which is local, which is global. Each has its own purpose. And then we have this concept of higher mode effects on tall buildings, especially, which we will also focus. Then modal analysis should be run before anything else. We always recommend our students and our colleagues here that if you're creating a model in ETABS or whatever software you're using, even before running the dead load, run the model first. Make sure that the properties are right. Make sure the structure is right. Make sure the model is right. If the model is right and the properties are not good, that means structure is not good. So we need to go step by step to make sure that what we are dealing with is correct, reasonably correct, before we start applying loads and doing all of the rest of the thing. So modal analysis is actually kind of a precursor to most of the analysis that we will do later, response spectrum, time history, and everything, even for wind, and so on. So we will look into that. And as you know, these animations are always fun to watch. From ETABS, you can get a lot of data, and they keep adding these rows. Before there only used to be 3 rows, now there are 5, 6, 7 rows. They keep adding more information that can be extracted from the modal analysis. And there are some interesting things here added recently, which lead to the higher mode computations. So you can see here that from this data, you can get the basic factors like natural period, frequency, and so on, participation factor, load participation factor, mass participation factor, and so on. So on this slide, when you get the notes, then you can go into the detail of what the purpose of each of these analyses is, and you can also read the documentation from ETABS. There's a lot of discussion about this there. So the point is that there's a lot of information, insight into the modal analysis alone before we go into the other ones. So mode shapes, to me, are fundamental to understand the structure. Of course, natural frequency number is one, but the mode shape gives us far more information, far more insight into structure if we know how to read it. Just like the doctors, if they know how to read the EKG or ECG, then they can quickly see what's wrong with the patient. Same way, we should be able to see the mode shapes and just see what's wrong with the structure, or it's good or not good. So we can detect the symmetry, the unsymmetry, we can detect the local modes, we can detect so many things. So let's look into those one by one. First of all, is your model trustworthy? Because once you created the model, how do you know that the model is good and that you haven't made any gross mistakes? And I have so many examples over the years where people have made gross mistakes in the model, did not detect it, and they went as far as to the site. There was one case particularly which is of note, that a structure was designed and the foundations were very heavy, and the contractor complained that this foundation seems to be too heavy, it's not possible, the structural engineer didn't pick it up. And when they went back, they found that they had applied the steel mass by mistake to the concrete elements. So everything mass was very heavy. Had they checked the initial periods, they would have immediately determined that this is not possible. Anyway, so you can check the missing stiffness, missing mass inaccuracies, boundary condition inaccuracy, which is quite common. And we can also look at the connectivity errors, structural irregularity, and symmetry validation. So much can be done by looking at these two parameters. Let's look at them. So you can see here that this is a 45 story building, and we are looking at various mode shapes. And then the second one, there's a second mode, as you can see, there's a torsion there. And then the third one, and you can see now the higher modes are coming in. The structure is deforming in higher mode. So you can watch now the modes, and there's a lot of information in each mode which we will analyze one by one. So just want to give you from a real building how you can look at those modes, the lower modes and higher modes. Okay, so let's start with a very simple structure, symmetrical structure. It's a 20-story building. It's within the rigid frame structure range. It's a little bit flexible, but I've started that. It's not too high, it's not too short. It doesn't have a shear wall, doesn't have anything, but it is within the general limits of rigid frames. So moment resisting frames. So we start with a very symmetrical model of this one, reasonably sized, and see what happens. So if you look at the initial periods, you will find here that we have the first period, initial period equal to 2.26 seconds, a little bit longer than it should be because structure is not restrained by shear walls. Second one, please. And then it's moving in one direction, and the second one is moving in the other direction, but also both of them are translational. And the third one, you will see, is moving in rotation, is rotating. This is the most typical response we should expect from a symmetrical building. First two modes being translational, each in the weaker and the stronger direction, and then the torsional mode as a third one. So this should be the order that we're typically looking for in buildings. Not always to get it, but this is what we should be looking at. Okay, let's look at the same modes in plan so it's more clear. So it's moving in X direction as the first mode, just complete translational. Second one, please. And that is moving in the Y direction, completely translational. And the third one is moving in rotation, which is pure rotation about the center. So from the rotational mass movement, there won't be any mass participation, much mass participation coming because it's rotational. Other two should be giving the higher mass participations in this case. And we can also look at those modes in the sequence. So in the sequence, like for example, first mode along X, which is the first mode of the structure also. Then second one is the second mode along X, but it's the fourth mode in the order. And that is you can see, and then the next one is the third mode in the X direction, and it's the seventh mode in the order, and the 10th mode and the fourth mode in the X direction. So you can see as we go higher, the modes are becoming more complex, the movements are more complex, the initial period is dropping, frequency is increasing because they have higher stiffness attached to them. And because of higher stiffness, they also generate higher forces because, as you know, force and displacement are proportional. So by looking at the modes, this is the ideal order, 1, and then 4 and 7 and 10 for the watch direction, and the other direction will be 2 and so on. And then torsional will be the same way. So we can look at about 12 modes for this building, should be enough. Okay, let's see, we make it slightly irregular. We add one shear wall on one end of the building and then see what happens. And then now you can see here, we are looking from the top, and we will see that the first mode does not change because the wall in this direction is just out of plane, does not add any resistance, and it almost did nothing. So in out of plane, the wall is as bad as anything, so it didn't do anything. But when the second mode, y direction, came, then the wall held on. It did not move together with the frame, so the whole building now revolving or rotating about the wall. So the stiffness center shifted toward the wall, mass centers remain the same, we have eccentricity, and then we can see, and then this one is rotating about the wall. The third mode is still torsion, which is rotating now about the center, kind of. So this is a true sort of indication of an unsymmetrical building where the second mode or the first mode will go into torsional or rotational. So if any one of the first two modes go into rotational, means that we have irregularity, plan irregularity in the structure. Let's say we introduce a vertical irregularity. We put two walls and we put one wall shorter than the other. This will create highly complex dynamic response because now part of the structure up to the 8th floor is symmetrical in y direction, but it's not symmetrical above that, so it will now shift the vertical stiffness center from the center to the right and so on. So it's now we are creating highly irregular structure. And if we look at the model response for this one, so we can see here the first one is like that because both walls are moving and it's rotating now. And then the next one, and then third one, the last one is becoming very complicated. Some parts are moving this way, some part are moving this way. There's no pattern because the lower part tends to be symmetrical, upper part is not. So the movements are now becoming highly unpredictable, kind of, and the force distribution cannot be predicted by a typical 2D analysis or typical sort of structural response. It will be more complicated than that. So vertical irregularity in a building of this kind will be probably more harmful or more difficult to manage than the plan irregularity, which we can see clearly. So vertical irregularity, let's look at this video for different modes. So we are looking at the first mode. So I put all the modes here so we can watch them as they transform. So after that, the first mode, this goes to the second mode, and then from that, and then we go to the third mode, rotation, and then you can see here, and then we have the next mode, fourth mode, and then we have higher fifth mode. Please continue. Yeah, like then now you can see the structure is deforming in very irregular manner, and the last mode that you will see is even more complex. So now some part of the structure is moving, some is not moving. So the forces, displacements, everything will be highly unpredictable in this case, especially when combined with ground motion, which are coming from different directions, and they will activate the structure modes in different contributions and different manners. So here you can see very clearly that vertical irregularity of a building like this is going to make the response pretty complicated. Okay, so different stiffness along X and Y. Now this may not seem to be a major problem because the structure is symmetrical about X and Y independently, but the problem is that the two stiffness are now very different. And the structure response, when real earth ground motions will be on at any given angle or even wind, then this structure, which appears to be symmetrical about each axis, is going to be performing not so well when we have excitations at an angle. So let's go to the next one and let's look at the modal response. The first mode is like this, but look at the initial period is 2 point something, and then the next one is 1 point something. So which means the second direction is very stiff along Y, and the X direction is very weak stiffness wise. So if you have one full order of difference between the two modes, that means the stiffness is very different in two directions. And when we have inclined excitation, this response will not be predictable because the two directions are not close to each other. So the lesson from here is that the two-directional response for the first modes or most of the modes, we should try to keep it similar. Not identical, difficult, but similar, of the same order, not 2 times or 50% different, because that will create, once again, an irregularity, directional irregularity, which is often missed in a structure of this kind. We do not, because the structure is very long, for example, and one direction we didn't provide enough walls, and then we rely on the frame, other direction we have walls, then the structure becomes, especially structures which are long in plan and have different stiffness, are more susceptible to irregular dynamic and wind response. So next point we come to that not all modes are created equal. That means we have to filter out the noise, because when you make a structure, you have all kinds of components there and everything is vibrating. So it's quite possible that some things are vibrating before the structure is vibrating, or they are vibrating in between the modes, and they will disturb or disrupt your main structural response computations. So that's why we need to be vigilant to detect the modes which are noise, or which are important, but not from the global point of view. They are important in their own right. So let's look at that. So finding the real story among the vibration is to make sure that when you look at the initial period, it should be reasonable in a certain number, and you look at the mode shape and it should be in a certain order. So if the order is out, or the frequencies are not progressing systematically in a certain order, on a certain sequence, then means something is wrong in between. So left-hand side is a normal building. The second one, I just put a small canopy on top of that. And here you will see that the canopy, or the top structure, will start to vibrate, move before the main structure, or will oscillate in a natural, so it will attract the first mode and second mode to itself. And the structure is now stiffer than this one. So if you look at the first two modes, those modes belong to the canopy, not to the structure. Although structure is moving a little bit too. So now the mass participation ratios will be different. And now you're looking at, if you normally in a building like this, left-hand side, the first mode will probably carry about 80% of the mass. In the right-hand building, the first mode will carry maybe 4%, 5% of the mass. So it's suddenly your understanding of the first, second, third mode will now be different. And if you're doing pushover analysis, for example, and if you by default select the first mode, then it won't be right, because first mode on the right-hand side will only select the top canopy and not the structure. And it will be, the target displacements and everything will be incorrect. So we have to be careful to see that the modes are global for the global response. For local response, we could look at those separately. So for a case like this, probably it's unnecessary to model the canopy in this global structural system and just apply it as loads. Is the structure good enough to check the pulse? So that means you need to, now we have come to the kind of a conclusion that we need to make sure that the initial period numbers are reasonable. For example, tall buildings, people say the initial frequency should be number of stories divided by 10, which is not always true. Actually, it is slightly less than that, and a lot of data has been collected, and there are many rules and many formulas to check that. In general, observed buildings have a shorter initial period than computed, because non-structural stiffness comes in, and there are other things that we could not estimate properly. We've used cracking factors and things like that we will talk later. So we need to make sure that we estimate it well. Then this, to me, is the most important slide of today's talk, that we need to arrange the modes in a certain sequence to understand what's going on and get the full picture. That means we should not look at the numbers of the modes in the sequence they are reported by the program, but in the sequence that we are looking for in each direction. And as soon as the sequence is out, or the drop from one to the other level is not reasonable, something is wrong with the model or the structure. So for example, like I showed you earlier, the first mode in the weaker direction should be 1, 4, and then 7. And if that is not the case, that means there is a vertical irregularity somewhere that is pulling the modes away. And here in this case, the orders are not the same. So there is something in the building that altered that. Similarly, the second row should also be in sequence. If it is not, that means we have something in the structure that is altering the sequence. Same is the case with the last one. Then we should look at how much mass is participating in each mode. The first three modes, in each direction should generally accumulate a lot of mass. If not, that means the higher modes and the local modes are corrupting the results, because generally speaking, for a building of this kind, 9 modes, 12 modes generally should accumulate enough mass. But sometimes you have to go to 30 modes or 40 modes to capture all the mass, which means there's a lot of local modes are also coming in, or there are far more higher modes with low stiffness which are also coming in. So we need to study, we need to arrange the modal response in a table like this, put the natural period, put the mode number, put the mass participation, everything, and then study this, because this picture can tell you a lot about the structure. And we normally always do that in the projects and also ask our students to create this for their class projects. So far we talked about earthquake and modal response, but modal response is also important for a lot of other things. If you are going to put base isolation, tuning, modal response is important. Tune mass dampers, modal response is important. Damage detection, I will talk about that, is important. Monitoring the structure, health monitoring, modal response is important. Wind engineering, very big relationship between the natural periods and the wind forces generated, especially the crosswind response is very important. So the tuning of the wind by mass dampers or whichever we attach is very much related to the natural periods. So this is some of the things other than that we can do. Response spectrum analysis, which is a derivative or is derived from the modal response, and it's one step next to that. So let's spend a little bit time on that. So from the ground motion equation that I showed you earlier for a single degree of freedom or this system, we can actually compute now the response, the displacement for a given damping, given mass, given stiffness. For those three things given, we can, for a given ground motion acceleration, we can determine the displacement and its derivatives. And that's the thing. So if we do that, let's say there's a ground motion on the top, we can then use the damping ratio, let's say a certain damping ratio. We put that in the equation, we put the mass, we put the stiffness, and we can get that. And from then, we change the damping ratio, change the natural period frequency, and then we get a second one. We change the frequency again, and then we get the third one. And then we pick the maximum ordinate of each of the displacement from each of these different natural period computations, and we plot them on a graph, and that becomes our response spectrum. I think everybody knows that. So that response spectrum becomes our key to determine the structural response. But let me mention this. Professor Wilson, who helped develop this one when I met him a couple of years ago, and he has said it many times in his blogs, and he started this long time ago, and he says that I regret starting the response spectrum method at that time, because it has so many sort of inaccuracies or so many conceptual compression of the things that it becomes, it's already used a lot, but there's a lot of debate about the relevance of this in the current day and stage. But anyway, assuming that we still use it, we can go ahead. So for a ground motion, for each ground motion, we can generate our response spectrum like this. For example, this is a response, different intensity, different PGA. We can generate the response for the maximum credible earthquake, the design basis earthquake, service level earthquake, and those response spectrum then can be used back into the analysis. So that's the story here. And response spectrum is affected by the soil, type of soil, because the ground motion from the rock coming all the way to structure is heavily influenced by that. And in Bangkok, recent earthquake has shown that this is a very important magnification or that we have to consider. Damping ratio, because the response spectrum is derived from a damping ratio and a natural period as the primary input, because mass and stiffness being constant, these two can change. And you can see here that the change of the damping ratio significantly changes the response spectrum. So an assumed wrong damping can heavily underestimate or overestimate the response. In fact, one of the things that a lot of researchers are saying that this 5% damping that we assume is too high. Real structures, especially the new ones, have much less damping, maybe 2%, maybe 2.5, maybe 1%. So if that is the case, then you can see that the response spectrum that we use to compute the forces will be far less than the actual response of the structure for a low damping. And the difference is very big, as you can see from here, from 2 to 5 and 5 to 10. From 2 to 5, the error is too big. So if we assume 5% and the structure only has 2%, the response experienced by the structure, especially at the longer period, will be very big difference. So this is something that has been observed, and it's now being sort of focused a lot, especially since the recent collapse of the building in Bangkok. So that brings me to the higher mode effects. The higher modes that tall buildings have, they behave very differently than the first modes. Typically, most of the design methods and design procedures are based on the first mode response. But if you go to ETABS, recent ETABS, they have added a new output at the last column, which gives us the modal separation seismic response using response spectrum analysis by giving you factors that you can use to multiply with the individual modes and get individual mode response rather than let the program combine the modes by some combination method. So when you separate the modes separately, you can get the response for each mode independently. And that's how you do that in ETABS. Once again, I will not go into that much detail, but more information is available on how to do that. So ETAB added this a few years back when the higher mode separation became important. And from that, you can now see that for building of this kind, you can separate the response for each mode, and you can see that the patterns of the forces generated, story moment, story shear, are very different. They are not the typical one that we normally assume. So the drift is very different for each mode, even though the sum may be like that, but the individual modes give a very different story. And similarly, the moment and shear are very different. And you can see here that there are the top of the building where we assume a small shear, typically that's how we think, gets a peak. And moment also gets a peak in the middle or somewhere. So depending on the building height characteristics, the higher modes can alter the way the story moments and story shears and the forces on the shear wall are acting, especially on shear wall. So the assumption that we can have more reinforcement and more thickness at the base and we can reduce as we go up actually may not be correct, because we may need higher thickness and reinforcement at some portions in the wall and upper stories. So that's one of the observations from this thing here. Now, higher modes, once again, you can see a huge change in this one. We have gone to more modes rather than first three, and you can once again see the patterns are very different. Now, the response spectrum method may be able to add those modes and give you the total response, which may be correct, but the problem starts here when we go to the nonlinear response, because the R factor that we use to reduce the response, strictly speaking, is really available in the first mode, because that's where the yielding is occurring at the base of the wall. And it's not really available at the higher modes, and higher modes have a much higher stiffness, so yielding with that will be not there. So with that in mind, when you compare the nonlinear response of a structure, the higher modes are contributing a lot. And in a traditional method, we reduce the total response spectrum by R, reducing all the modes by the same factor. But in fact, the higher modes should not be reduced by the same factor, because there's no yielding or no ductility available for them to be reduced in the same proportion. So that leads us to believe that the actual shear especially the shear, if you look at the shear in the structure, is much higher than what the R factor divided, total response divided by R gives us. And this is something that could be cause of a lot of difficulties in the tall buildings. So that's why many methods are being revised using these multi-mode analysis with the partial R or different R for each mode. So this is another subject that we can talk about sometime. Also, the response spectrum and the frequency modal response or the frequency initial period have a very close relationship. So this is showing two different response spectrums here. One is from Philippines, one is from Bangkok, and you can see here that their response spectrums are very different. The Bangkok one peaks at 2 seconds. Manila peaks at these close to 0 seconds. This is typical of a solid rock base and a soft basin type. But the important thing is that, let's say if it's a tall building, 50-story building, the first modal period will be around 5.5 seconds for this one, and it has 50% mass participation, and the ordinate is very low, so it will have very low contribution from the response spectrum. The higher mode, the second mode, is about 2.5 seconds, 30% mass participation. It will attract a very large force, even though the percentage of the mass is less, mass participation less, but the response spectrum ordinate is high, so you get higher. And then 10%, but the ordinate is much higher. And remember, as I said, these two modes may actually not yield, so they should not be divided by R, so their contribution becomes much more significant in that way. For a 20-story building, 25-story building, the Bangkok response is actually very, very critical because it peaks at that point. So the first mode will give a higher than the higher mode. So the relationship between the response spectrum of the location and the ground motion that derived it and the natural periods is very critical. And this has been shown recently in the Bangkok earthquake. That is the data that we got from Professor Pennins and Professor Thirapan. So this one shows clearly that the response spectrum from the earthquake was very different, and it sort of kind of remained peaked at this range of so any building that has a natural period between that was heavily influenced by this response spectrum from this particular ground motion, very long flat area in the middle, and very small in the 2-story, 1-story range. So what are the things that affect the modal response? Modal response is influenced by, of course, mass and stiffness. Those are the only two things that can influence it. The structure, the attachment, and the occupants will influence the mass, and the stiffness will be influenced by the tower, podium, basement, foundation, and soil. So all these stiffness contributions will be needed. And then, if you look at the stiffness is contributed by the material, by cross-section, by members, and by foundation. So we need to make sure that we include all these stiffnesses correctly. And many of these stiffnesses are actually nonlinear, because after the damage occurs, they change, which means that the natural period will change when the damage occurs. A new building, after a few years, after an earthquake, after a windstorm, the stiffness will change because of the damage. So all of that can occur. And so we need to be able to determine the natural period of a structure at a given time, at a given situation. And that brings us to structural health monitoring and modal properties. So, which means that over the period, over the life of the structure, we should monitor the change of the natural period of the building. And there are a lot of ways to measure that, because this will not be the same that we assumed. The damping will change and stiffness will change, so the whole response of the structure can change. So we can see a key concept that we have to measure the frequency of the structure because it changes over time, and then we need a long-term plan to measure them. And that's why in almost all major structures these days, bridges, especially tall buildings, others, the sensors are put in to measure the natural vibrations and acceleration and so on, and stresses and strains. And this is very similar to going back to the health metaphor. This is a stress test. Young people don't need to do that, but people of my age, when we go to the hospital, they ask us to stand on the treadmill, and then they attach a lot of sensors, and they measure the change in the heart rate and the pattern as you run or walk, and then they take you to the peak as far as you can go until you cannot take it anymore. Then you bring you back. So they say, okay, how much stress the body will take, and then they tell you, okay, you are ready for marathon or not ready for marathon, and so on. And same is the true for structures. If you put the sensors, we can monitor the same way, and we can always know where the structure is going and how it will respond when it is stressed. So natural frequencies, like I said, is a pulse. So we need to measure the pulse, as we are measuring the pulse of the human being by trackers and by health things. So it's just, and we can do that by measuring. There are many ways to measure the natural periods of the structure. I don't have the time to do that. We'll discuss that some other time. We can detect the damage by change of the natural period. One of the most common way to detect the damage is by measuring the natural period today and then after 1 year and after 3 years and so on. So if we measure it, if there's a change in natural period and the mass hasn't changed, that means stiffness has changed. Stiffness has changed because damage has occurred. And this is a model that we propose, that where we can link the buildings to our sensor system and to the whole cloud system. We proposed that in Philippines a while ago because they have sensors, acceleration sensors in each building. So we did some studies, got some data. I'm just going to go through quickly to show you what's possible. So after that, you can get the data from the site, you can measure the natural periods, you can plot all these things, you can get all the data from that, you can link it back to the X and Y direction, pre-damage and post-damage, post-earthquake damage. You can determine those numbers and you can say, okay, this much degradation or damage has occurred because the natural period has changed. So based after that, you can see where it happened and you can do the whole nonlinear stuff. So now, which means full cycle is possible. By putting the sensors, by recording the natural period, measuring it over time, measuring it after an earthquake, having the model, we can complete the whole evaluation immediately. Without checking the building, we can see what will happen. Let's wrap up then. So, as I was saying, fitness trackers, modal analysis, they are similar. You have now, everybody's so concerned about the fitness. We should be equally concerned about the modal analysis and structural response. So let's put some trackers on the structure, either physical or even metaphorical, you can say, by looking at these properties. And this is a kind of a one-on-one correlation between what the tracker is giving about the human health and what the modal response can give us for the structural health. Once again, I leave it for you to read it when we send the slides to you, because it's just saying that there is a kind of a rough correlation between almost everything that the tracker reads and the modal response similarly can help us find. So let's conclude this by saying that estimating, understanding, and including dynamic response in the design is the key to the reliable performance of structures, both for wind and earthquake, and also for vibration, floor vibration, walking, and all that kind of stuff, even blast. But it all starts with the modal analysis. So I think with that, we come to the end. Thank you so much, everyone.